way, right? So we're looking just at this ellipse. So what we're really interested in is the values of the function on the ellipse. Oh, sorry, not this one, right? The one which goes through 0. Yeah, it's just bad drawing. It's a bad drawing day. But this one. But you see what I mean? And 1/2 would be then, and it's not 1/2, it's like 1/3. Sorry, but you see what I mean? It's not to scale, it's not parallel, it's not. It's a very qualitative picture, not very precise. Kind of abstract, like Picasso, the way Picasso would approach it. Okay, but I hope you see what I mean. That as you vary, the point is that when you go to the next one to the right, the value will increase. When you go to the next one to the left, the value of the function will decrease. But we are interested not in the values everywhere. We are only interested in the value on and values on that ellipse. So in particular, we now know that here and here, that these are the 2 points of intersection of the line f equals 0 with our ellipse. Here and here, the function is equal to 0. Here and here, the function is equal to 1. Here and here, it's equal to 1/3, and so on, right? So now, how can we use this picture to find where the function takes maximum or minimum values? Well, the point is that for sure, we can see from this picture, it's quite clear that f equals 0 is neither maximum nor minimum. Why? Because this line, we can move both to the right and to the left. When we move it, and we'll still have some points of intersection with our domain, not this domain, sorry, with the ellipse, with our curve. Right? If I move it even by 1/3, I can move it even by 1/3, and I still have intersection. So that cannot be maximum value, because here the value 0, here is 1/3. Likewise, say this one would be f equals negative 1/3. So from here, I can also move along this curve to the left. So I can shift my parallel line to the left, decreasing the value. So 0 is neither maximum nor minimum. Likewise, this is neither maximum, this one is not, this one is not. So at first it looks like none of them are maximum or minimum, right? So the point is to find the points where this qualitative argument doesn't work, where it breaks down. We have to find the points where you can no longer move it to the right or to the left. In what sense? Of course, you can always move it to the right and to the left, but you cannot move it and still have non-empty intersection with your curve. For example, you have a line like this, which is one of the level curves, but it's totally outside of the scope of our problem. In other words, there is no intersection between this line and this curve that we're interested in, right? So those guys are excluded from our consideration anyway. Okay? And so the point is to find the points where you cannot move to the right or to the left and still have a non-empty intersection. And the point is, for most of these lines, for all the lines which I have drawn, you have 2 points of intersection. So as you move further and further and further to the right, okay, let me just make it slightly more realistic looking. Somebody have a question? No. Okay. As you move it, you still get 2 points, 2 points, 2 points, 2 points, 2 points, and then boom, there's this 1 point. Something happens at this point, the intersection. Instead of getting 2 points, you get just 1 point of intersection. Right? In other words, you have 2 points, 2 points, 2 points, but they get closer and closer to each other, and they converge at this point. And suddenly, you get a very special point. This point is a point where the intersection is just this 1 point and not 2 points. Right? You see what I mean? It's just 1 point like this. And likewise on this end, the same thing. You have intersection of 2 points, and 2 points, and the next one is 2 points. I'm just unable to do parallel lines today. 2 points, 2 points, and then suddenly, boom, there is this one line where it intersects at 1 point only. And for these 2 points, my previous argument actually breaks down. You see, because when I was here, I could argue that this is not the maximum minimum because I could move this way, I could move that way, and when I move a little bit, I would still have a non-empty intersection with my curve. But when I'm here, I can certainly move it to the left, so I can decrease the value. But I cannot move it to the right. It's kind of frozen here. What do I mean that I cannot move it to the right? Of course I can. I can move it, but if I move it by any small amount, epsilon, or any other small amount, there will still be a line like this, but it will not intersect my curve. Right? So that second argument breaks down. So that means that this is the maximum value, because I cannot move it anymore to the right. You see what I mean? Likewise, this is the minimum value, because I cannot move it anymore to the left. So what are these special points? Well, now we know enough about level curves and things like that to realize that these are precisely the points where this line is tangent to this level curve. Right? So this is the case when this is a tangent line. And likewise, this is the case where this is a tangent line. Okay? And what does it mean that this is a tangent line? It means that the normal vector to this level curve is proportional to the normal vector of this line. Right? So we have found that the maxima and minima are the points where the level curve of the function f of xy, which in this case is 2x plus y. In this case, the level curves are lines, but in general, they're not going to be lines, they're going to be some curves, where the level curve of the function which we want to maximize and minimize, so f is function that we want to maximize or minimize, okay, is tangent to our curve, which is this h of xy, which is equals 1. So it is x squared plus 4y squared equals 1. So that's the given curve. That's the given curve. So the point is that we are given, in this exercise we are given 2 functions, but they play very different roles. There's a function f and there's a function h. Function f is the function which we want to maximize, minimize. Therefore, we kind of look at all level curves of that. H is the second function, is the function which defines the curve and also defines the domain. If actually our original problem was about the interior of that curve, the way I started talking about this. And for this function, we only interested in one level curve. That's the curve where we want to maximize and minimize f. But the interesting things happen at the places where the two curves are tangent to each other, as I explained. And what does it mean that they're tangent to each other? Well, in this example, the level curves of f are lines. So it's clear what we mean by saying that it's tangent, because we talk about tangent lines. But in general, if you have 2 different curves, there is also an obvious notion of being tangent. It just means that the tangent lines to them are coincide, right? Or in other words, the normal lines to both of them coincide. So this means, in other words, the normal lines. So we are points where the level curve of f is tangent to our curve. Maybe I should say these are the points. These are the points where the normal lines to f of xy equals k and h of xy equals 1 are the same, coincide. So how do we check that? Well, we know that the normal lines are given by the direction vector, the normal vector to that curve, which is a gradient. So equivalently, we can say that the two gradient vectors should be proportional to each other. These are the points x0, y0, such that nabla f at x0, y0 is equal to lambda times nabla h for x0, y0. And that's the equation that will give us those points. What is the meaning of this equation in our case? In our case, at each point we have a normal vector to the line f, f equals k. That's the vector 2, this is nabla f. Actually, nabla f is very easy to find, it's 2, 1. It's a vector 2, 1. The two partial derivatives of f are 2 and 1. Let me do it in red so that everything is in the same color. This is nabla f at this point. And nabla h is a vector which is normal to the curve. So in this case, the curve goes like this, so the normal vector will go like this, right? So that's nabla g. Clearly, at this point, they are not proportional to each other. And they shouldn't be, because these are not the points where the two level curves are tangent to each other. They intersect with a certain angle. They are not tangent. But at this point, the two normal vectors suddenly become proportional to each other. So this is one, and this is the other. They become proportional, you see. So that's, and likewise, same thing here. So that's why, that's why at these points, we get the maximum minimum values. So let's find these points. Are there any questions about this, first of all? Yes? What's lambda? Very good point. So lambda is the coefficient of proportionality. We don't know it a priori. This is, by the way, a very important point, because some of you made this mistake on the midterm. If you have two vectors, each vector spans a line, right? So what is the property of the two vectors for the lines to be the same? It's not that they're equal, right? That's not that they're equal. They should be proportional. Because if you have a, if you have a vector, you get a line. But if you take twice that vector, you get the same line, right? So the condition is much weaker. The condition is that the two vectors are proportional to each other, then the two lines coincide. And what does it mean that they're proportional? Proportional means that one of them is equal to some number times the other, and we call that number lambda. So that's the coefficient of proportionality, which in this case is called Lagrange multiplier. I'm thinking about another name. Lagrange multiplier. And this method of finding the extremal points is called Lagrange multiplier method, after a great French mathematician, Lagrange. So, any other questions? Let's see how you'll probably see it better when we do it in this example. So, let's see what this equation looks like in this example. So, what is nabla f? Nabla f consists of two partial derivatives of f, and those are very easy to find. They're just 2 and 1. And what's nabla h? These are the two partial derivatives of that function, x squared plus 4y squared. So it's going to be hx and hy, going to be 2x and 8y. And now the equation that we want is that 2, 1, that's the left-hand side, is equal to lambda times 2x, 8y. More precisely, since here I wrote x0, y0, let me stick to that, and let's write also x0, y0. But of course, when you do your calculations, you will oftentimes just write x and y without worrying about this index 0. Here I write x0 and y0 to emphasize that we're talking about a particular point, x0, y0, and not about general values x, y. So, but this is not just one equation. This is a system of two equations because you have two components of these vectors. So there are two equations. 2 equals lambda times 2x, and 1 equals lambda times x0, y0. Right? So let's remember one thing, which is that lambda is unknown. We are saying that they're proportional to each other, but we don't know a priori what the coefficient of proportionality is. So what we need to do here is to solve these equations for x0, y0, and also lambda. But you shouldn't forget that actually you're solving it not on the entire plane, but you are solving it on that curve only, right? We're interested only in that curve now. That's very important. So far, I've written the equation as though x0 and y0 were an arbitrary point. But in fact, it should be a point on that curve. That curve C. So we have to add one more equation, which is the equation of that curve, which is x squared, x0 in this case, plus 4y squared equals 1. So in fact, you have three equations on three variables, x0, y0, and lambda. If you just write these two equations, it would mean that you look everywhere. But you have to constrain x and y, or x0, y0, by imposing the original equation of this curve. Okay, so now it looks more meaningful, right? Because you've got three equations and three variables. And usually, generically, if you have three equations with three variables, you're going to get one solution, or you get finitely many solutions. That's what's going to happen here. Let's find this. Let's find the solution. So first we can express x0 and y0 in terms of lambda, and then we can substitute x0 and y0 into the third equation, and we'll get one equation of lambda. So that's the simplest way to solve it. So from the first equation, we find that x0 is 1 over lambda, right? For the second equation, we find that y0 is 1 over 8 lambda. And now we put them into the third equation, and we get 1 over lambda squared plus 4 times 1 over 8 lambda squared equals 1. Okay, so that means 1 over lambda squared times 1 plus 4 divided by 64 equals 1. And that's going to be what? So this is 1 over 16, so that's 17 over 16. And from this you find that lambda squared is equal to 16 over 17, right? Is that right? 17 over 16. right? Because you take it to that side. 17 over 16, and that means that there are two solutions for lambda. Lambda is equal to plus or minus square root of 17 divided by 4. Okay, once we know what lambda is, we can find x0 and y0, right? So now we find x0 is equal to 4 over square root of 17. Well, there are 2 points. First of all, there are 2 points, right? So for each, let me do it slow. Let me not mess it up. Each solution for lambda will correspond to a particular point. And of course, we kind of know that we should get 2 points. We expect to get 2 points. One will be the maximum, and the other one will be the minimum. So the first point is lambda equals square root of 17 over 4. Then x0 is 4 over square root of 17. And y0 is 1 over 8 of that. So it's 1 over 2 square root of 17. Right? And the second point, so that's this point. That's this point. And the other point is going to be this with the minus sign. 4 over square root of 17 minus 1 over 2 square root of 17. Okay. So lambda equals minus square root of 17 over 4. x0 is minus 4 over square root of 17. y0 is minus 1 over 2 square root of 17. And well, in this particular case, it's clear which one is the maximum, which one is the minimum, because we can see it clearly on the picture. But in general, it may not be so obvious. So what you should do is you should just substitute them into your function and calculate the value. And the one for which the value is bigger will be the maximum, and the one for which the value is smaller will be the minimum. So in this case, f is going to be, you have to substitute 2x plus y. So that's going to be 2x plus y. So it's like 8. It's going to be 1 over square root of 17. And here will be 8 plus 1 half. Right? So that's going to be 17 square root of 17 over 2. Because you got 17 over, this is square root. And here the function will be just, actually, in this case, but here, see, I was too fast. I kind of, I know it is correct, right? So it will be just minus of that, so minus square root of 17 over 2. And so here that's the maximum, that's the minimum. So that's the solution, yes?
In general, we say that for your picture there, for the maximum, the gradient of your f and the gradient of the function have the same sign.
That's right. They point in the same direction. So lambda is positive. Right. And when it's minimum, they should be opposite. Right, exactly. It's always like this. If they are pointing in the same direction, that's the maximum. So that's actually a very good question. That we can actually tell by looking at which direction the two vectors are pointing. Or in other words, what is the sign of lambda? If the sign of lambda is positive, it's a maximum. If the sign of lambda is negative, it's a minimum. And geometrically, actually, I did not draw the picture, but the picture would be like this. This would be the white will be the gradient vector for the function g, and but now the red one will not go this way, but red is always the same. Right? It's 2, 1. So that's number f. And here, see that here they're opposite, whereas here they are pointing in the same direction. Any other questions about this? Yes? Right. So this. That's right. So that's right. So you're talking about the question is about the level, the red ones, right? So the red lines are the level curves of the function f, which is 2x plus y, right? So we could look at the equation f equals 2x plus y, right? In 3D, that would be z equals 2x plus y, right? So in fact, because this function is linear, the graph of this function would be a plane, right? And that plane actually can be very easily illustrated here, right? So let's say it's this plane, right? So now what are the level curves? So I'm going back to the same drawing which I did a couple lectures ago, right? What are the level curves? We can draw level curves. So the level curves are just what you get sections which are parallel to the floor. Sections by planes which are parallel to the floor, right? So here's one of them. Here's another. I should have drawn in red, but you see what I mean. This will be. So these are the level curves for the function f. But again, so you can think of the level curves as being part of the graph, but you can also think of them of their projections onto the xy plane. So what I have drawn on that picture are the projections onto the xy plane. You see. So I'm writing them as equations. F equals something. For example, f equals 0, or f equals 1/3, or f equals negative 1/3, f equals 1, and so on, right? If you like, you can think of the plane, which is the graph of this function, as one which is obtained by assembling those lines, but in a kind of a each time you have to lift it by the height, which is equal to the value of the function. So only this one, the one for which f is equal to 0, will remain on the xy plane, and these ones will be elevated, and those guys will be lower, right? Just like here. So let's say if the xy plane, was, so that this one was, let's say this one is f equals 0. So then this one will, let's say this is f equal 1/3, and so on. So they're all elevated. So it's like, think of a sort of staircase. I mean, it's not really a staircase, but if you think of just step 1/3, then this is a collection of lines. But it doesn't make sense to draw them in 3D because they're given by equation on just x and y. So that's why I'm drawing their projections onto the floor, onto the xy plane. You see? Yeah. That's right. That's a very good question. So far, we were lucky that the domain, or more precisely the boundary of the domain, was represented by one equation only. So now I would like to, sort of as a last example, to look at a kind of a mixed case, where you can have several components in the boundary, and some of them could be linear, and some of them could be curved like this. So let's say a very simple generalization of this example would be